this lecture, I'll be talking about double integrals, where the region we're integrating over is more general than just a rectangle. I'll begin by talking about some general properties of double integrals. These double integral properties are not something I like to discuss too much because basically you're going to assume these properties anyway. So for example, the first property is that if I have a double integral of a constant times a function, I can take out the constant. This is a property we had with single variable integrals, and so it's nothing different. Here the same thing, if I have a sum of two functions that I'm integrating, I can integrate over each function separately and then add. And the same thing with subtraction. And these properties in particular, and this last property I'll talk about, all are only true if we assume all the integrals exist in the equations we have. So this last one I can describe in a little bit more detail. What we have is a region R that we're integrating over in the xy plane. So again, this double integral is really representing a volume. So we have, this is the base of the solid, and the top is some function z equals f of x, y. And what this is telling us, this identity, this property, is that we can split this region into two pieces. So we can split this R into two pieces. And if I call the two pieces R1 and R2, then I can integrate over R1 and integrate over R2 and add the values of those two integrals. So here I want R1, R2, the regions to combine to give you the region R, and for these regions to be non-overlapping. But as long as you just split the region into two pieces like this, we can integrate over each of the regions separately and then add, and we'll get the value of the double integral of f of x, y over all of R. So those are the properties. And let me move now to a definition. I'm not really interested in worrying too much about type 1 region as far as the name of that is concerned, but the region itself, it looks like this. We have a function on top and bottom here, y equals g1 of x and y equals g2 of x, and x itself is between two numbers, say a and b. So we have x between a and b, so we have the line x equal a here and the line x equal b here, giving us the bounds on x and also giving us the bounds from the left and right of the region. On the bottom we have a y equals g1 of x, and on the top we have y equals g2 of x. So again, I'm not going to refer to this as a type 1 region, but I do want you to know that we can handle regions that look like this, and this is something we're going to handle right now. So the idea is that we want to integrate from x equals a to b, and then as we take a vertical line here, we can see we want to integrate then from y equals g1 of x to y equals g2 of x, from the bottom to the top. Here are some other pictures of this type of region. This is basically what we were looking at before, this region. This one has a little bit of difference in that at one of the endpoints here, the values agree on the top and the bottom, the y equals g1 of x and the y equals g2 of x, so they come to a point here. And here we see coming these regions, these curves, y equals g1 of x and y equals g2 of x, coming to a point on both the left and the right. But all of these are the same type of region. We basically can say in every case that x is going between a and b, and y is going from g1 of x to g2 of x. The other type of region we want to discuss is this situation, where now we have y going between two numbers c and d, and for each fixed y we draw a horizontal line, and you can see that x is going to go from this left curve, x equals h1 of y, to x equals h2 of y. Again, I will not refer to that as a type 2 region, but in general, there are some books that refer to it that way and others that don't. So here are some other pictures of this region. We have, again, y between two numbers c and d, and the left curve being x equals h1 of y, and the right curve being x equals h2 of y, and that's true in both of these pictures. So we basically want to integrate this type of region, the first region we talked about, by saying x is going from a to b. So we have x going from a to b. And for each fixed x, again, we want to think of y as going from g1 of x, from the bottom to the top curve, y is equal to g2 of x. So going from g1 of x to g2 of x. Notice I always go in the direction of the positive axes here. I'm going from a to b because the x-axis goes in this direction. And I'm going from the bottom curve to the top curve because the positive y-axis goes in this direction. So on the second type of region, we have y between c and d. And so we have y going from c to d here. And then for each fixed y between c and d, we want to think of x as going from the left curve to the right curve. So again, I'm going the direction of the positive x-axis. I'm going from the left to the right. So x equals h1 of y to x equals h2 of y. And that's what we have here. This you can read on your own. It's basically describing how you can do this in 2 steps, but it's basically just what I said in reverse order. So I actually prefer to do step 2 first, as I discussed, where we're going to go ahead and think of x as going between a and b, as in this picture on the bottom here. And for each fixed x, we draw a vertical line, and we see that y is going from the bottom curve g1 of x to the top curve g2 of x. So here's a picture with the slice we did earlier, where we see that if we fix x here, that y is going from the g1 of x in the back here to the g2 of x in the front here. So that will be the range on y. And that will give us what we want for the volume of this slice, because we want to take y going from g1 to g2 when we integrate, and the function z equals f of xy is going to give us the height of that slice. And again, we have a delta y, and then which later becomes a dy, and we get the double integral the way we've been talking about. Here's the same type of information for the other type of region we're talking about. We want to go ahead and integrate from c to d for the y, so y is going from c to d, and for a fixed y, we draw a horizontal line, and we see that x is going from the left curve here, x equals h1 of y to x equals h2 of y. So let's try some examples, keeping all this in mind. The first one is to write a double integral with limits of integration indicated that represents the volume of a solid above the region R, bounded by y equals x and y equals x squared in the xy plane, and bounded below by the surface z equals 2 minus x squared minus y squared. Now I can give you a picture what this solid looks like, but it's not terribly helpful. So the main thing you want to do to get a hold of this problem is to go ahead and see what's happening in the xy plane. Figure out what the region R is that we're talking about here, which is bounded by y equals x and y equals x squared. Well, we know how to graph y equals x and y equals x squared, so let's just do that. So y equals x squared is this parabola. Y equals x is this line. And so the region bounded by those, we can see, is just this region inside here. So we want to integrate over x and y inside that region. It doesn't make too much difference which one we do first, but it's a little bit easier to go ahead and say x is between 0 and 1. This is the point 1, 1 where these two intersect. So x is between 0 and 1, and then for each x between 0 and 1, draw a vertical line and see that y is going from the bottom curve, y equals x squared, to the top curve here, the line where y equals x. That's just a little bit easier because these are already written in terms of y as a function of x. So this is the region we're talking about. And we set up this double integral again with x going between 0 and 1. For each fixed x, we imagine drawing a vertical line. and y is going to go from the bottom curve, y equals x squared, to the top curve, y equals x. This is the top of the solid, so this is just the base. The top of the solid is apparently this graph z equals 2 minus x squared minus y squared, which is a paraboloid hitting 2 on the z-axis and opening downwards. But this is what's left of it above this region. So one thing maybe to check if this is really a volume is that this needs to be greater than or equal to 0 inside this region. So the largest x and y can be are when x and y are both 1 here, and 2 minus x squared minus y squared is going to be greater than or equal to 0 there. It's going to equal 0 at 1, 1. So that's the smallest this gets, so it is in fact above the xy plane. So we are getting a volume, and that volume will be this double integral. Let's try another example. So here we're faced with just calculating the value of this double integral. We have e to the x cubed we're trying to integrate with respect to x, and some region we're integrating over in the xy plane. Now, you could do this presumably without drawing the region, but maybe not, because we would have to integrate e to the x cubed. So try as you may, it's not actually easy to integrate e to the x cubed. So in fact, there is no nice antiderivative for e to the x cubed. So you're going to have to do something else here. And when we're faced with a double integral where we don't know how to integrate it, there's going to be 2 approaches we can take. And one that we're talking about today is going to be to interchange the order of integration. In other words, to change this from a dx dy to an integration where we have dy dx. Now, why would that be helpful? Why would it help to have a dy dx here? Well, if we want to integrate whatever the limits are of e to the x cubed dy, the e to the x cubed is a constant because we're integrating with respect to y then. So think of this as being 17, and so if I could put a dy dx here, I'm just integrating 17 dy, and that's just 17y. So as long as this is a constant, which it will be if we're integrating with respect to y, this is going to be easy to integrate. So the idea is to change the order of integration so we can do the first integration and hope that after we do that first integration, the second integration becomes easy to do as well. So let's see what happens. So the first thing we need to do is to figure out what the region is that we're integrating over here. We can see y is going from 0 to 1, and for each fixed y between 0 and 1, we want x to go from the square root of y to x equals 1. So x equals the square root of y should be on the left, x equals 1 should be on the right. So this is a picture of the solid, not helpful again so much, but in the xy plane what we're going to have is this picture. Here, this came from first graphing x equals the square root of y, but realizing that that's the same thing when I square both sides as y equals x squared. At least as far as this picture goes, and we have this parabola then y equals x squared that I know how to graph. So that's this one, x equals 1 here, and that's just the graph of this line going straight up, and so we have x equals 1 there. So this is the picture of the region. Well, where exactly is the region here? So let's look at this. First, where is this point? This point is where these two intersect, when x equals 1 and y equals x squared. So when x equals 1, y will equal 1 from y equals x squared. So this will be the point 1, 1. So in this picture, we see that y is going from 0 to 1. For each fixed y, we draw a horizontal line, and x will go from the square root of y, x equals the square root of y, to 1. So x is going from the square root of y to 1, so we're inside this region here. So again, I draw a horizontal line, and we can see x goes from the square root of y to 1. So we're inside this region. This is the left curve, this is the right curve, and so this is the region we're talking about. Let me color that in. So this is the region we're integrating over in the xy plane, and now we want to switch the order of integration, and to do that, we want to look at what the limits should be. X is between 0 and 1 in this region, and for each fixed x, we draw a switch this line around and we're going to draw a vertical line. And this vertical line is going to go from y equals 0 down here to y equals x squared up here. So y is going from 0 to x squared. We're going from the bottom curve where y equals 0, the x-axis, to y equals x squared. So that's why I wrote the double integral like this. Again, x is between 0 and 1. For each fixed x between 0 and 1, we draw a vertical line again, and then y goes from the bottom curve, y equals 0, to the top curve where y equals x squared. We still have the same function we're trying to get, so we have e to the x cubed here. And now we just want to try to evaluate this double integral, where again, we know at least the first integration we can do fairly easily, because this is just a constant when we integrate with respect to y. So let's look at what we get. So since this is a constant, we're going to get e to the x cubed times y, where y goes from 0 to x squared. I plug in 0, I'm just going to get 0, so all I need to do is plug in x squared here, and I have e to the x cubed times x squared that we're trying to integrate. Now this is not terribly easy, but we can see that we can integrate this because when we take the derivative of x cubed, we have 3x squared, so we get something close to what we have here. And so this calls for us to do a substitution. So we'll do a u substitution here. We'll take u to be x cubed, and then du is going to be 3x squared dx, since du over dx is 3x squared. And then if I solve for x squared dx here, we can see that's just 1/3 du. So we have that information that we can use, and I will then replace this x squared dx we have here with the 1/3 du, because x squared dx equals that. I'll replace the x cubed here with the u, since u equals x cubed. So to put this in perspective here, we have the integral of e to the x cubed x squared dx. I'm replacing the x squared dx with du. I'm replacing the e to the x cubed with e to the u. And we have then this integral, which we can integrate. The integral of e to the u is just e to the u, so we get 1/3 e to the u plus some constant. But an antiderivative for this is e to the x cubed over 3, and so I can use that to evaluate the integral we have down here. We get e to the x cubed over 3 evaluated from 0 to 1. Don't forget to plug in both 0 and 1, because when we plug in 1, we're going to get e, and when we plug in 0, we get e to the 0, which is 1. So this part evaluated from 0 to 1 becomes e minus 1. So we have e minus 1 times a third. That gives me e minus 1 over 3, and that is the value then of this rather messy integral we started with, so this double integral up here. So again, the lesson here is when you have a double integral that looks difficult to integrate, think about switching the order of integration to make the process a little bit easier. Let's do one last example. Write a double integral that represents the area of the region bounded by y equals x minus 1 and y equals 1 minus x squared. Where here I've given you the picture, y equals x minus 1 is the line, the slope 1, and the y-intercept minus 1. And then we have the parabola y equals 1 minus x squared, which intersects the y-axis at 1 and then opens downward. Now, I put area in quotes here because usually when we set up a double integral, it's representing volume. So let's get back to that in a little bit. So first I want to figure out what to do with this region, and I can integrate dy dx or dx dy, but notice if I try to integrate dx dy, so I want to first figure out what's going on with y. Y is going between minus 3 and 1. So I would say y is going between minus 3 and 1, and then I would draw a horizontal line to see what's happening with x. X is going from the left curve to the right curve. So x is going from this parabola to the line. Well, we'd have to solve for x here. X is going from, looks like x is going from the square root of 1 minus y, but that's not quite correct because x is negative over here. So it's going from negative the square root of 1 minus y. And then it's going to here we solve for x and we see x is y plus 1, so it's going to y plus 1 here. Unfortunately, that's not the case everywhere. If I draw a horizontal line this up here, I can see that I'm going now from the left curve, being the parabola we had, to the right, which is the same curve, the parabola we had. So the limits of integration really would be here, the minus the square root of 1 minus y, and then plus the square root of 1 minus y here. And what we'd have to do if we're going to integrate dx dy is to split up this integral right along this line here. So from minus 3 to 0, we're integrating from this parabola we talked about to this line, and then from 0 to 1, we're integrating from part of this parabola to the other part of the parabola. That sounds a bit difficult. So let's not do it that way. Let's go ahead and do it dy dx instead. So what happens when we look at this with dy dx? We have x going between minus 2 here and 1. And we can check that these are really minus 2 and 1. At minus 2, it looks like we have a minus 3 for y. See, if I plug in minus 2, I have a minus 3 there. If I plug in minus 2 squared, that'll give me a 4. 1 minus 4 is negative 3. So this minus 2 minus 3 is correct. And this point, is this really where it looks like it is? So it looks like x is 1 and y is 0. Yes, we can see if we plug in x equals 1, we get y 0 there and 0 here. So indeed, x is going between minus 2 and 1. And for each fixed x, we want to draw a vertical line to see what's going on with y. And we can see y is going to go from the bottom curve here, that line, to the top curve, the parabola. So y is going from x minus 1 to 1 minus x squared. So if we set this up, we have x between minus 2 and 1, between minus 2 and 1 here. For each fixed x between minus 2 and 1, y is going from the line x minus 1 to the curve, the parabola, 1 minus x squared. And again, we can see that does not depend on where this line is. As long as it's a vertical line between x equals minus 2 and 1, the bottom curve is going to be the line, and the top curve is going to be that parabola. So this would give us the limits of integration we need for that region. Now, why did I put a 1 here? Well, recall from what we did earlier that if we're taking the volume of a solid where we have the base given by a region in the xy plane, and the solid just has height 1, that the volume is just the area of the base times that height 1. So it's the area of the base times 1, that's just the area of the base. So again, this is just going to give me the area of this region then. So if I put a 1 there, it's going to give me the area of the region. Let me also comment that we don't need to have that 1 there. That 1 is telling us we have 1 dy dx. Well, that's the same thing as just putting dy dx. And so we could also write the answer this way as far as